Hello students, so today we will discuss about nanoscale optical interactions. Now, the electric field associated with a photon, can be confined by using a number of geometries. So this can be confined with the help of geometries. To induce optical interactions at nanoscale. Now, the optical field can be localized in the nanoscale. The optical field can be localized at nanoscale, and the localization can take place both axially or laterally. So if we say the nanoscale localization in the presence of EM field, then can have two divisions, axial division and lateral division. This axial division has again two subdivisions. One is called evanescent wave and the other one being surface plasma. Evanescent wave can again be further subdivided into total internal reflection and optical waveguides. The lateral part, lateral localization, has again two different configurations. First one is called aperture-less confinement, of a nanoscale tip to enhance local electric field, and the other one being confinement by aperture near propagation. Confinement by aperture near field propagation. Evanescent wave are derived from photon tunneling in the case of waveguide. So associated with photon tunneling. In the case of waveguides, and it generates the surrounding medium of low refractive index. Generates surrounding medium of lower refractive index, where it decays exponentially in axial direction away from the waveguide. So there is an exponential decay also associated with it. Exponential decay, and this decay, it extends up to 50 to 100 nanometers, and can be used to induce nanoscale optical interactions. And this evanescent waves are mainly used in fluorescent sensing with near surface selectivity. So typical use are in fluorescent sensing. Now, another example of nanoscale optical interaction is coupling of two waveguides by evanescent wave. Coupling of two waveguides by evanescent waves. So when we have, say this is waveguide 1, and this is waveguide 2, so there is a coupling going on. So this is 1 and this is 2. Coupling will take place. So here, this is the coupling. Now photons launched in waveguide 1 tunnel into waveguide 2. So the phenomena that is occurring is photons which are launched in waveguide 1, they tunnel to waveguide 2, and they are used as something called directional couplers. For switching of signal, mainly for signal switch in an optical communication network. So also it has been proposed for sensing applications, where sensing produces a change in photon tunneling from waveguide 1 to waveguide 2. So there are basically, it falls into the category of optical communications or optical networking, and sensing. These are the two main application of these directional couplers. Another example of the geometry coming into play for an evanescent wave is given by total internal reflection involving propagation of light through a prism. There is a prism of refractive index n1, and so light propagation takes place through a prism of refractive index n1 to an environment of lower refractive index n2. So n2 is less than n1. So we draw the prism like this. So it will be theta here the light repasses, whereas if we have so this is theta 1, and it may so happen that the angle of incidence is a little less, so it is say theta 2, so it reflects internally, and it also happened that the third case where after reflection it actually again moves to the environment. This is theta 3. So if we consider theta C as the critical angle, then theta 1 is less than theta C. Theta 2 is equal to theta C, where exactly the light, the photon beam goes into the prism, and theta 3 is greater than theta C, that light comes out. So this is what is known as a TIR, total internal reflection, for this case. Now at the interface, the light refracts and passes to the second medium at a sufficiently small incident angle. So what happens when the angle is greater than the critical angle, light beam is reflected from the internal surface. So this is what is called TIR, light beam being reflected from internal surface, and this is what is popularly known as TIR. So this critical angle is again sin inverse the ratio of refractive index of the two medium, and usually it is seen that the N1 is 1.53 for say standard glass, and N2 we take as 1.33. We will consider it as an aqueous buffer, and if we consider these two values, then the value of critical angle comes out to be around 61 degrees. Now, even under the condition of total internal reflection, a portion of the incident energy penetrates the prism surface as an evanescent wave. So you can see that a portion of incident energy, it penetrates the prism surface as an evanescent wave, and enters the environment to contact with the prism and further enter. Now its electric field of the amplitude, if we consider the electric field, say it has got an amplitude E2 of the incident wave, rather put it as Ez incident wave, and it exponentially decays with a distance z into the surrounding. So exponentially we can write the formula as equal to exponential minus z by dp, where dp is equal to a lambda divided by 4 pi n1 sine square theta minus n2 by n1 whole square, to the power half, and this is nothing but the penetration depth of the electric field, and the penetration depth for crucible light, of course, and the penetration depth is between 50 to 100 nanometers. Now the evanescent wave energy can be absorbed by an emitter, a fluorophore, to generate fluorescent emission. So evanescent wave energy can be absorbed by a fluorophore to give FL emission. However, because of short-range decay of evanescent waves, specimen near the substrate can be imaged.